Hey students, welcome to lecture number 5 of Linear Algebra 2. So today we want to talk about the properties of determinants, which we introduced last time. So recall, if we had a square matrix, an n by n matrix A, then we defined the determinant as this sum here. And what this meant was that if we start with some matrix, for example this matrix here, like this 3 by 3 matrix, then what we considered were all so-called patterns where we needed to choose one entry in each row and each column. So for example, this would be a pattern, and then in this case we wrote this pattern like this. So in the first row I choose the first entry, in the second row the third entry, and in the third row the second entry. And this gave us some permutations, which we denote by sigma. So this is 1 sigma 1, 2 sigma 2, 3 sigma 3. And permutations were elements in this set Sn, which were all bijective maps from the set 1 to 3 up to n to 1 to 3 blah blah n. And in this case, this map sigma is the map which sends the set 1 to 3, 1 to 3 to, well, 1 gets sent to 1, 2 to 3, and 3 to 2. And then, so we sum over all possible choices of these patterns, meaning we sum over all possible choices of these bijective maps. And then we multiply with the sign of this, and the sign of this was minus 1. So this was minus 1 to the number of inversions of this sigma. And these number of inversions correspond to pairs I, j, such that I is smaller than j, but sigma of j is smaller than sigma of I. So, and this corresponds in this picture here to the number of crossings. So in this case here, in this one example with this sigma, the number of inversion is 1, and therefore the sign of this sigma is minus 1. And then we take the product over all chosen entries, which in this case would be 1 times 9 times 13, multiplied with minus 1, and then take the sum of all possible choices of these patterns and permutations. And today, the goal is, so the goal today is to prove some properties of these determinants. And one particular goal we want to achieve is to show that a matrix A is invertible if and only if the determinant is non-zero. So, and for this we need to prove some lemmas and propositions, and we will start with a lemma on inversions. Namely, the statement is if I have a permutation in Sn, then the number of inversion of sigma equals the number of inversions of a sigma inverse. But in this picture here, this is somehow clear because sigma goes in this direction and sigma inverse goes in the other direction with the same picture. So the number of crossings is the same. But let's do this precise. So let's prove this. So what was the number of inversions of some permutation sigma? So this is a number of I and j's such that this I is strictly smaller than j, but the sigma of I is greater than sigma of j. And now we do some renaming. So we say set. So we now denote by k the sigma of j and by l the sigma of I. So this is now L here and this is k, so L is greater than k, and therefore the inverse of k is j and sigma inverse of L is I. So here this I is sigma inverse of L. So here L is greater than this, and this is smaller than sigma inverse of k. So you see that now, so the number of ij with this property is the same as the number of L and k, such that L is greater than k, but the sigma inverse of L is smaller than the sigma inverse of k. So therefore, this is exactly the same as the number of inversions of the sigma inverse, which, because it's just a renaming of these variables. Okay, and this we want to prove, use to prove the following, namely that if we have a matrix A, then the determinant of A equals the determinant of A transpose. And remember this notation here, AT, so the transpose of A was obtained by changing the rows and columns. So for example, if I have a matrix 1, 2, 3, 4, then the transpose of this just means that the first column becomes the first row, the second column becomes the second row. And now we want to show that the determinant of this matrix A equals the determinant of the matrix A transpose. Okay, so let's do this. So A, let's say A, so this is a proof. A has entries A, J, and A transpose has the entries Bij. So in other words, Bij is just Aj, I. And now we want to calculate the determinant of A transpose. So what is this? Or maybe first let me recall. So maybe we can copy this here. Oops. So here this is the determinant of A with the entries Aij. And now the determinant of the transpose, well, it's the same definition, but now let's give it different names. So instead of sigma we use a tau. So this is the sign of tau. And here we take the product j from 1 to n of bj tau of j. And remember, so this, by this comment here, because this is the transpose, so it's just changing rows and columns. So this is A tau j, comma j. And now let's make a renaming again. Let's say the tau j we call k. So this is the sum. Tau goes sum over all permutations tau. The sign of tau. And now, so when we take the product here, j goes from 1 to n, and we call this tau j k. Since this tau is a permutation, this means this is a bijective map. So taking the product over all j going from 1 to n, this also means that this k runs from 1 to n. So this is just the same as the product k goes from 1 to n. And now it's a k, and here it's tau inverse of k. Yeah. Because so if k equals tau j, then j equals tau inverse of k. So we have this. But now, so we had this lemma here, which stated that the number of inverse, the the number of inversions of some sigma equals the number of inversion of sigma inverse. So in particular, this also means that so from this we get that the sign of sigma equals the sign of sigma inverse. So here, now instead of taking the sum over all tau in sigma n, we could also make a renaming and say that sigma we call now tau inverse. And if we sum over all inverse of tau, it's the same as taking the sum over all sigmas. And now here we would have the sign of tau inverse, but this is the same as the sign of sigma by the lemma before. So this is lemma. And here we just have the product now. K goes from 1 to n, ak, and sigma k. And this is the same as this here, with the only difference that k is now called I here. So this proves that the determinant of A equals the determinant of A transpose. And here in this example you see that 1 times 4 minus 3 times 2 is of course the same as 1 times 4 minus 2 times 3. Okay. So now, first some notation. So now what we want to show is that the determinant is linear in each row and also in each column, which then follows from this. So for this we want to introduce some notation. So let's start with an n by n matrix A. And now we choose a row, some L, we choose between 1 and n. And now let's assume we have some vector in Rn. And what we want to define now is a matrix where we take the matrix A, and in the lth row we plug in the entries of x. So let's say x is x1 up to xn. So we want to define what we mean by A. In the lth row we plug in the vector x. So if A is again a matrix with entries aj, then here I have A11 in the first row up to A1n. And then in the lth row, so this is the lth row, I plug in x1 up to xn, and here I have an1 up to ann. And this is what we mean by this entry here. So this is again a n by n matrix. And now with this, so we want to make the statement that the determinant is linear in each row. And this can be phrased as follows. Namely, if we have a matrix A and we choose some row, then this map FAL, which now sends a vector in Rn, to the determinant of the matrix A, where we replace the lth row by x, then the statement is that this map is linear. So this will be, so this is homework 5, exercise 1. So you need to check again that, so what does linear mean? So you need to check these two properties. If you take two vectors, x and y, then you have this. FALY for all x and y in Rn. And also, if you multiply with a lambda, it's lambda times FALX. So for example, what does this mean? This means if I have a matrix, some matrix here, and I multiply the lth row with some lambda, then the determinant of this matrix is just also multiplied by lambda. And also here, if I have, if I add 2 rows, then we also see that we can add the determinants here. Okay, so this is this, and this you will show in the homework. And for this, of course, you need to use the definition here and see what happens if you look at the part when I equals L. So in the else row you do something, and then you need to show why these two conditions are satisfied. Okay, so let's do one example for this notation. So if the matrix A is this matrix here, and we now consider the case L equals 2, so in this case this map, which is now denoted FA2, so this is a map from R3 to R, where we send the vector x1, x2, x3 to the determinant of the matrix. Well, now we write this into the second row of A, so the first row is the same, and here we have x1, x2, x3, and here we also don't change anything. So we send this vector to this determinant, which is a real number. And in the last video we calculated the determinant of a 3 by 3 matrix, and the idea was we take this times this times this, plus this times this times this, plus this times this times this. So here we have 9 times x2 plus 14 times x3 coming from these, plus 3 times 8 times x1. So this is 24 times x1. So these were the patterns with a positive sign, and with negative signs we had this, this, this. So for example, this gives minus 21x2. We had this, this, and this. So this is 18, so minus 18x1 minus this, this, and this. So minus 8 times x3. So in other words, this is just 6 times x1 minus 12 times x2 plus 6 times x3. So in other words, this is the vector x1, x2, x3 multiplied with a 1 times 3 matrix, 6 minus 12, 6. So in this specific case, we see that this is indeed a linear map, because in this case it's just multiplication with this matrix here. Okay. So now this proposition, which states that if I have a matrix A and I swap 2 rows in the matrix A and call the new matrix B, then the determinant of A is minus the determinant of B. And here we just give the proof idea. So if I want to calculate the determinant of A, then I need to choose patterns and sum over all possible choices of pattern. So let's say I choose this row and this row. So let's say this is the matrix A, and since in each pattern I need to have at least one element, exactly one element in each row, so for example I could choose these 2 elements and now assume that I swap these 2 rows to get the matrix B, then this pattern exactly corresponds to a pattern where I now choose this element here and this element here. And you see here that this gave us an inversion. When some choice is on the top right of some other choice, then this always increases the number of inversions by 1. So if there's no inversion here, then there will be inversion there. And the other way around, if there was no inversion here, so like something like this, then there will be no inversion here. So you see for each pattern, because I swapped just these 2 rows, I get exactly a change of sign in the definition of the determinant, and therefore the determinant of this matrix is the negative of the determinant of this matrix. And one consequence of this is the following, namely if I have a matrix A where two columns in the matrix are the same, then the determinant of this matrix is 0, because if I swap these two columns, then of course I don't change the matrix because they are the same. If I swap these two rows, then I don't change the matrix because these two rows are the same. But due to this proposition, I change the sign of the determinant, so the only possible choice for the determinant is 0, because just 0 satisfies the property that minus 0 equals 0. And also, if we do the same with columns, because we saw earlier that the determinant of a matrix A equals the determinant of the transpose, so the transpose is a matrix where the rows becomes columns, and therefore also if I have a matrix, so the first statement is if I have a matrix and I swap two columns, then I also change the sign of the determinant, and also if I have two same columns, then the determinant of the matrix needs to be 0. Okay, and now so these swapping columns and also adding columns to each other, like in this linear map before, this we did in linear algebra 1 when we were solving linear equations. There the goal was always to bring a matrix into its row-reduced echelon form, and for this we used 3 row operations, which I want to recall now. So recall that there are 3 types of row operations, which we can do for, well, in linear algebra 1 we did it for arbitrary m times n matrices, but now we focus on n times n matrices, but still there are these 3 row operations. So the first row operation was that I could add a multiple, here the multiple will be called lambda, of one row to another row. The second one was if this lambda is not 0, then I could always multiply the matrix, the one row with this lambda, and the third operation was to swap 2 rows. And so now the statement we have here is what happens if I do this, so what happens to the determinant by using these row operations. And so let's say I have 2 matrices A and B is obtained from A using these row operations. And also recall that A and B, we had this notation that A and B are row equivalent if I can obtain A from B, when I obtain B from A by using one of these row operations. And so the statement is now if B is obtained from A by using R1, meaning I add a multiple of one row to the other, then it has the same determinant as A. So this row operation doesn't change the determinant at all. The second statement is if I multiply a row with some lambda, then I multiply the determinant by some lambda. And this we already saw, because this linear map FAL is a linear map, and this is one statement which is contained in this. So, and the third one, if I swap 2 rows, then we saw before that the determinant gets a minus sign. So if we want to prove this, no. So proof. So again, number 2 and number 3 are okay. So these we saw before. Number 3 is this statement here, and number 2 is exactly that this map here is linear, because if x is the lth row of this matrix here, and I multiply this with some lambda, so this this here is the determinant of the matrix where I multiplied the nth row with lambda, and the statement here is that this equals lambda times the determinant where I just have the row there without the lambda. So these two statements are okay. So we just need to check the first statement. So let's say I have a matrix A. So this is A, and let's call the first row R1 and up to Rn. And now I use R1, so I want to use this notation here. So this matrix is row equivalent after using this row operation R1 to the matrix which we now call B. And what we do is, so R1 was adding lambda times the jth row to the ith row. So here I still have R1, but somewhere I have the row j, so there I have Rj, and I have the row I, and now here the row is Ri plus lambda times Rj. And here I have Rn. But this is the same as R1, Rj, Ri, Rn plus lambda times R1, Rj, Rj in the ith row and Rn. Because this is just the addition of matrices. But now we also know that the determinant is linear in the rows. So here notice this is a matrix A. So the determinant of B is, so the determinant of this is the determinant of this plus lambda times the determinant of this. So this is determinant of A plus lambda times, so let's call this C, determinant of C. But here in the matrix C we see that there are two rows which are the same, so therefore, so this is 0, so this doesn't play any role here, so the determinant of B is just the same as the determinant of A, and this is what we wanted to show. Okay, so yes, so let's do one example for this. So let's assume we have this matrix A, and in linear algebra 1, one exercise, for example, would be to calculate the row-reduced echelon form of this matrix. And for this we use these three row operations. So let's do this in this example and always keep track what is the determinant. So in this case here, the determinant is, of course, because this is just a matrix A, so the determinant is determinant of A. So now what would be the first step here? Where the first step would be to subtract the first row from the second and third. So what we would do is we do row operation 1, meaning -1 times the first row we add to the third and second. So we use R1 twice here to get 1, 2, 3. Here we have 0, 0, 1, 0, 2, and 3. And by the proposition, because we used R1, the determinant is still the same. It's still just the determinant of A. And now what we want to do is swap these two rows. So we swap them. So what we do is R3. So this will give the matrix 1, 2, 3, 0, 2, 3, 0, 0, 1. And since we used R3, the determinant gets a minus sign, so this now has determinant -A. And what we want to do now is minus 3 times this one we can add here to remove these 3's. But this is again R1. So we don't change the determinant. So it's 0 here, 0, 0, 0, 1. So it's still the determinant of, so it's still minus the determinant of A. And now we multiply the second row with 1 half. So we use R2 with lambda equals, so we use R2 with lambda 1 half. So we get the matrix 1, 2, 0, 0, 1, 0, 0, 0, 1. And now the determinant is minus 1 half determinant of A. And yeah, and now we subtract minus 2 times this from there. So this is again R1 to get this matrix here, the identity matrix. And since we used again R1, we don't change the determinant, so this has determinant minus 1 half determinant of A. So this is now the row reduced echelon form of A. And well, what is the determinant of this? So this is I3, and the determinant of the identity matrix, or in general, if I have a matrix where I just have entries on the diagonal, then there's always just one pattern I can choose. I can just choose the things on the diagonal, because every other choice would give me at least 1 0 in the product. So here the determinant is just a product of the entries on the diagonal. So of course this is not, so this is the determinant of I3. So this determinant is 1. So we see that minus 1 half times determinant of A is 1. And of course this is also the determinant of the row reduced echelon form of A. So what we get is that the determinant of A in this case is minus 2. But also what we see is, if we start with an arbitrary matrix A here, and we do these row operations to end up with a row reduced echelon form of A, then what happens to the determinant? Well, in these steps with R1, they just stay the same. In R3, I just multiply by minus 1. And using R2, I always multiply with this lambda, where this lambda in R2 is non-zero. So if the determinant at the beginning is non-zero, then also the determinant, well here, so this is a determinant of the row reduced echelon form. So if we start something here which is non-zero, then also this will be non-zero. And so we see that, notice, in general, if I have two row equivalent matrices A and B, so B comes through row operations from A, then the statement is the determinant of A is non-zero exactly then when the determinant, or it's 0 exactly then when the determinant of B is 0. So in particular, when B is the row reduced echelon form of A, which is always row equivalent to A. And with this, we can now prove our main goal of today, namely the statement that a matrix is invertible if and only if the determinant is non-zero. So we want to show A is invertible is equivalent to the determinant of A is not 0. So let's see how this works now. So assume that A is invertible. So we now want to show this direction here. A is invertible, and then the determinant is non-zero, so A invertible, we learned in linear algebra 1, means that the row reduced echelon form of A is just the identity matrix. And by the observation before, so the determinant in particular of this is 1, so it's non-zero. And then we saw that if the determinant of the row reduced echelon form is not 0, then also the determinant of A is not 0. Because the row reduced echelon form is row equivalent to A, because we can always go there by using these row operations starting with A. And now the other way around. So we want to show that if it's non-zero, the determinant, then A is also invertible. And so what we show is that if A is not invertible, then this also implies that the determinant has to be 0. So if A wouldn't be, so if A is not invertible, well, this meant that the rank of A is smaller than n, and the rank of A was exactly the number of non-zero rows in the row reduced echelon form. So if A is not invertible, then this means that in the row reduced echelon form of A, we have that the last row is the 0. So, and we know that if a row of a matrix is 0, then also the determinant needs to be 0, because all possible choices needs at least one choice in the last row, so all products vanish, and therefore the determinant of the row reduced echelon form of A is 0. And then we see again that in this case also the determinant of A needs to be 0. So in other words, if A is not invertible, this would imply that the determinant is 0, and therefore if the determinant is non-zero, then we get that A is invertible. So now we proved this main goal of today's lecture, but we will also state another theorem, which we will prove next time. So the statement is already what I mentioned at the beginning of last lecture, that if we have two matrices A and B, which are n by n matrices, so I can multiply them and get again an n by n matrix. So then the determinant of this matrix is just the product of the determinant of these two matrices. And in particular, if A is invertible, then the determinant of the inverse is given by 1 over the determinant. So the proof of this, so number 1 we will do next time, but number 2 follows from number 1. So if A is invertible, then A inverse exists, and we know that A times its inverse is just the identity matrix. But then by number 1, the determinant of this product, well, this is the determinant of the identity matrix, which is 1, but this should be the same as the product of A times the determinant of A times the determinant of A inverse. So in other words, the determinant of A inverse times the determinant of A is 1. And therefore, if we divide by the determinant of A, we get that the determinant of A inverse is exactly 1 over the determinant of A. And also we can divide by the determinant of A because we just learned that the matrix A is invertible exactly then when the determinant is not 0. So we don't divide by 0 here. Okay, so, and one consequence of the first statement here is also now the following. So in the third lecture we talked about matrices of linear maps. So recall that if we have a finitely generated vector space V, and I have a linear map from V to V, then for a basis, for example B1, we were able to define this matrix of F with respect to B1. So we, in general, we defined it like this. So it was a basis B1 to B1, and if these two bases are the same, we just denoted it like this. So this gave a matrix, n by n matrix, if the dimension of this vector space V is n. And we could also do this for another basis B2, which gave a different matrix. But here the statement is, if we have a linear map F, and we have two bases of this vector space V, then the determinant of this matrix of F with respect to the basis B1 equals the determinant of F, of the matrix of F with respect to the basis B2. So, and why does this follow from the theorem before? So these matrices were different, but we had the formula that the matrix of F with respect to the basis B1 was given by taking this change of basis matrix going from B1 to B2. Then I multiply with the matrix of F with respect to the basis B2, and then I can go back from B2 to B1. So we had this equality here. So here I have product of three matrices, and this matrix here, the change of basis matrix from B2 to B1, was the same as taking the change of basis matrix from B1 to B2 and taking the inverse. But now we see that if we take the determinant of this matrix, then by the theorem before, taking the determinant of a product is the product of the determinants. So here we get that this is the determinant of the matrix SB1, B2 inverse times the determinant of the matrix of F with respect to the basis B2 times the determinant of the matrix, the change of basis matrix from B1 to B2. But here we have the determinant of the inverse of this matrix here. So this determinant this is just 1 over the determinant of S B1 B2, and therefore these two terms cancel out, and we see that the determinant of this matrix is the determinant of this matrix. So even though these matrices are different for different bases B1 and B2, the determinant is the same. So this is really now, so with this we can really say that this this linear map F, we can assign to this a determinant by choosing just an arbitrary basis B, and then say the determinant of this linear map is given by the determinant of this matrix with respect to this basis. And this is exactly what we do here. So the definition is, if we have a finitely generated vector space and a linear map from V to V, and now B is any basis, then we define the determinant of the linear map F as the determinant of the matrix of F with respect to the basis B. And due to this corollary, it doesn't matter which basis we choose, because these determinants will always be the same. And this you will do for examples in the homework, where I give you different linear maps. One of them you already know from homework 2, and you should calculate the determinant of these linear maps. Okay, so what is open now is still to prove this statement here, which we now already used twice. So this we will do next time. See you then.